This video covers part 2 of section 3.7, division into cases. In this video, we're going to look at introducing cases into our proofs. Very often, in attempting a proof of a statement, even though the original statement may not involve a disjunction, we may want to introduce cases ourselves, as illustrated in the following example. So we want to prove for all integers n squared plus n is even. This has symbolic form for all n and z, n squared plus n is even. And so we'll start our proof. Suppose n is an arbitrary integer. We need to show that n squared plus n is even. To show this, we need to show there exists an integer k such that n squared plus n is equal to 2k. So we'll set up our two columns. We need to find a k and then verify that k satisfies our two conditions. Now ordinarily in existence proofs, to find what we're looking for, we either solve the propositional function or we use hypotheses to determine it. In this proof, solving the propositional function gives us k is equal to n squared plus n divided by 2, which we cannot conclude is an integer. So this approach doesn't work. We have no hypotheses in this proof except that n is an integer, which also doesn't seem to help. So at this point, it's not at all clear how to find the integer k that we need to find, since we do not have any additional information about n. To proceed further, we introduce our own cases. Since n is an integer, then we know that either n is even or n is odd. To prove the result holds for integers in general, we can prove it in each of these cases. So we'll start the proof over and introduce these two cases at the outset. So suppose n is an arbitrary integer, and now consider the two cases, n is even or n is odd. In each of these cases, we need to show n squared plus n is even, or there exists an integer k such that n squared plus n is equal to 2k. So we'll get started on case 1. Our hypothesis in case 1 is we'll suppose that n is even. We need to show there exists an integer k such that n squared plus n is equal to 2k. Setting up our two columns, we can now use our hypothesis that n is even to conclude that there exists an integer j such that n is equal to 2j. Then n squared plus n is going to be 2j quantity squared plus 2j, and after a few steps in algebra, we obtain this as 2 times the quantity 2j squared plus j. And now this looks like our propositional function with 2j squared plus j taking the place of k, so we can choose k to be 2j squared plus j. Moving over into the right-hand column, since j is in z and z is closed under multiplication and addition, then k equal 2j squared plus j is in z. And from the work on the left, n squared plus n is 2 times the quantity 2j squared plus j, which is 2 times our k. So the propositional function holds. So this proves the existential statement, so proves that n squared plus n is even, and this proves case 1. For case 2, we're going to suppose that n is odd, and we again need to show there exists an integer k such that n squared plus n is equal to 2k. Applying our hypothesis, since n is odd, then there exists an integer l such that n is equal to 2l plus 1. Then n squared plus n will be 2l plus 1 quantity squared plus 2l plus 1, which we can manipulate and rewrite as 2 times the quantity 2l squared plus 3l plus 1. And now this has the form of our propositional function. So we choose k to be the expression in parentheses 2l squared plus 3l plus 1. And as before, since l is in z and z is closed under multiplication and addition, then k equal 2l squared plus 3l plus 1 is also in z. And the work on the left shows that n squared plus n is 2 times the quantity 2l squared plus 3l plus 1, which is 2k, so the propositional function holds. This proves the existential statement once again, so proves that n squared plus n is even, and this proves case 2. Since we have now proved the conclusion in both cases, this proves the original statement. Now, introducing the two cases in the preceding example provide additional hypotheses that enabled us to prove the conclusion. Introducing cases is often helpful for this purpose, particularly for proofs involving numbers. For instance, for a statement involving a real number x, we could introduce the cases x is less than 0, or x is equal to 0, or x is greater than 0. Now, when introducing cases ourselves, we must choose the cases so that they exhaust all possibilities for the variable. That is, every element of the domain must satisfy one of the cases. In the preceding example, we know that every integer is either even or odd, so must fall into one of these two cases. Similarly, every real number is either negative, 0, or positive, so must fall into one of the above three cases. Although it is not essential, in most proofs, the cases should also be mutually exclusive, meaning that they do not overlap. That is, each element of the domain satisfies at most one of the cases. The cases listed above for a real number x satisfy this condition. It's possible, however, to consider cases which are not mutually exclusive, such as x is greater than or equal to 0, or x is less than or equal to 0, which overlap with x equals 0. While there is no requirement that the cases are mutually exclusive, if they are not, it may be an indication that dividing into cases is not warranted in the first place. The point of using division into cases is to gain additional hypotheses through the division, which may not occur when the cases are not mutually exclusive. The next two examples involve the absolute value function. So first recall the definition. The absolute value of a real number x, which is denoted with the two vertical bars, is defined by the absolute value of x is negative x if x is less than 0, but it's just x if x is greater than or equal to 0. According to the definition, the absolute value of a non-negative number x is just the number itself. The absolute value of a negative number, however, is the negative of the number. The result is the negative of a negative, which will be a positive number. So for instance, the absolute value of negative 3 is minus a minus 3, which is equal to positive 3. Since the definition of absolute value involves cases, proofs involving the absolute value typically involve division into cases as well. For example, we want to prove for all real numbers x, the square root of x squared is equal to the absolute value of x. This has symbolic form for all x in R. The square root of x squared is equal to absolute value of x. Before starting this proof, we need to make sure we understand the terminology and the notation. First off, for any positive real number a real number b is a square root of a, provided that b squared is equal to a. That is, the square of b equals a. This is just the definition of the square root of a number. As you're no doubt aware, every positive real number a has two square roots, one negative and one positive. For instance, negative 2 and 2 are both square roots of 4, since negative 2 squared is equal to 4 and positive 2 squared is equal to 4. The positive square root is denoted square root of 4 equals 2, using the radical symbol. The negative square root is denoted minus square root of 4, which is equal to minus 2. So we have to include a minus sign in front of the radical symbol. So when we write the square root of a with no sign in front of the radical symbol, we mean the positive square root of a. This is sometimes referred to as the principal square root of a. If we want to refer to the negative square root, we need to write a minus sign in front of the radical symbol. More generally, for any non-negative real number a, the square root of a refers to the non-negative square root of a, which means the non-negative number whose square equals a. So now back to the proof. So suppose x is an arbitrary real number, we need to show the square root of x squared is equal to the absolute value of x. As mentioned above, the notation square root of x squared represents the non-negative square root of x squared, which means the non-negative number whose square equals x squared. Therefore, to show the square root of x squared is equal to absolute value of x, we need to show that the absolute value of x is the non-negative number whose square is x squared. Since x is a real number, then we know that either x is less than 0 or x is greater than or equal to 0. So we need to prove the result in each of these two cases. And you'll see that the two cases correspond exactly to the two cases in the definition of the absolute value. So in case 1, we're going to suppose that x is less than 0. And we need to show that the absolute value of x is the non-negative number whose square is x squared. From the definition of the absolute value, since x is less than 0, then the absolute value of x is negative x, and since x is negative, negative x is positive, and hence non-negative. The square of the absolute value of x in this case is going to be the square of minus x squared, and when we square minus x squared, we just obtain x squared. This proves that the absolute value of x is the non-negative number whose square is x squared, so proves our result, the square root of x squared is equal to the absolute value of x in this case. For case 2, we're going to suppose that x is greater than or equal to 0. And we again need to show that the absolute value of x is the non-negative number whose square is x squared. From the definition of the absolute value again, since x is greater than or equal to 0, then the absolute value of x is just x, which is non-negative, since x is non-negative. Also, the square of the absolute value is just going to be x squared. So this shows that the absolute value of x is the non-negative number whose square is x squared. So again proves our result, that the square root of x squared is equal to the absolute value of x in this case. Since we've now proved both cases, then our result holds. For another example, let's prove for all real numbers x and a with a greater than or equal to 0, if the absolute value of x is less than or equal to a, then minus a is less than or equal to x is less than or equal to a. This is a result that I'm sure you're familiar with from pre-calculus, where you can rewrite an absolute value inequality as the double inequality shown. So our symbolic form is for all x, for all a greater than or equal to 0, absolute value of x less than or equal to a implies negative a is less than or equal to x is less than or equal to a. Now this result can be proved geometrically using the interpretation of the absolute value of x as the distance from 0 to the point x on a number line. Here we want to prove it algebraically using the algebraic definition of absolute value. So we'll start by supposing x and a are arbitrary real numbers with a greater than or equal to 0. We'll suppose the hypothesis, absolute value of x is less than or equal to a. We need to show our conclusion, minus a is less than or equal to x is less than or equal to a. Now this double inequality is actually equivalent to two inequalities with an and between them. So it's equivalent to minus a less than or equal to x and x is less than or equal to a. So to prove the double inequality, we have to prove these two single inequalities. Since x is a real number, then we know again that either x is less than 0 or x is greater than or equal to 0. So we need to prove the conclusion in each of these two cases. And again, we're picking these cases because they correspond to the cases in the definition of the absolute value. In case 1, we're going to suppose that x is less than 0, and we need to show minus a is less than or equal to x, and x is less than or equal to a. Now, since x is less than 0, then we know that the absolute value of x is going to be equal to negative x. Then substituting this into the hypothesis, absolute value of x is less than or equal to a, we just obtain minus x less than or equal to a. And multiplying this inequality by negative 1, we obtain x is greater than or equal to minus a. We have to flip the inequality around. Or we can rewrite this inequality with the minus a on the left, and we obtain minus a less than or equal to x. And so this is the first of our two inequalities that we need to show. Now, since x is less than 0 and 0 is less than or equal to a, by transitivity, we obtain x is less than a. And this is our second inequality, or close to our second, implies our second inequality. So we've then proved the two inequalities, minus a less than or equal to x and x is less than a, which implies the double inequality, minus a less than or equal to x less than or equal to a, which is our conclusion. And this proves case 1. For case 2, we're going to suppose that x is greater than or equal to 0, and we again need to show the two inequalities, minus a less than or equal to x and x less than or equal to a. In this case, since x is greater than or equal to 0, then the absolute value of x is just x. And then substituting this into the hypothesis, absolute value of x less than or equal to a, we obtain just x is less than or equal to a. And you can see that this is one of our two inequalities that we need to show. To obtain the second inequality, since a is greater than or equal to 0, then we know that negative a is less than or equal to 0. And then since negative a is less than or equal to 0 and 0 is less than or equal to x from this case, by transitivity we obtain minus a less than or equal to x. And that's the other inequality that we needed to show in our conclusion. So we've then proved the two inequalities, minus a less than or equal to x and x less than or equal to a. So we get our double inequality, minus a less than or equal to x less than or equal to a, which is our conclusion. And this proves case 2. Since we've now proved the conclusion in both of our cases, then the result holds.